This function here is the classic example showing you that the mixed partial derivatives are not equal at the origin. And the truth is, if you just compute the mixed partial derivatives, f sub xy versus f sub yx, they look exactly the same. It's just that they are not equal at the origin. How is that possible, right? Well, we'll figure that out. And in fact, this right here does not violate Clairaut's theorem because it does not satisfy the condition of the Clairaut's theorem. So we'll talk about that later as well. Let me get this right here for you guys first. To do so, firstly though, we have this expression when xy is not at the origin. Let me just do f sub x first, which is just the partial derivative of f with respect to x. So looking at this equation, we will have to do the quotient rule. Let me put the bottom function to the top. We get x squared plus y squared times the derivative of the top with respect to x. So do this, we get 3x squared y, and then minus, that's 1, and then y cubed, and then minus the top function, x cubed y minus xy cubed, times the derivative of the bottom with respect to x. So that will be 2x. And all over the denominator squared. And then let's just go ahead and simplify it. So this times this, 3x to the fourth y, and then minus x squared y cubed, and then plus 3x squared y cubed, and we have minus y to the fifth. Take this multiply, we get minus 2x to the fourth y, negative, negative, and that plus 2x squared y cubed, and then all over the same denominator. Okay, let's see, can we combine anything? Of course, this and that, so we get positive x to the fourth y, and then we also have minus x squared y cubed, and then plus 3 of them, so it's 2, and then we have 2 more here, so that's plus 4 of them, x squared y cubed, and then minus y to the fifth all over the denominator. So that's f sub x. Now, in order for us to get to f sub x y 0, 0, in fact, we also need f sub x at 0, 0. But I cannot just plug in 0, 0 into x and y because otherwise we get 0 over 0. So we will have to use the definition. This right here, remember, x is the variable, so we do the limit as h approaching 0, f of 0 plus h. You add h in the x component, and then the y stays 0 minus f of 0, 0 over h. This right here is where we have to use that from the original function. Okay, so this means I put h into all the x's, and then I put 0 into all the y's. But if I put 0 into all the y's, that is 0, that's 0, and then we have 0, so it's like 0 over h squared. So I will write that. Here we get 0 over h squared, which is going to be 0, minus this thing, which is that, by definition 0, over h. But that's 0 minus 0 over h is 0. Make sure you work this inside out. The inside is 0 already, and when h approaches 0, this right here will just give you 0. So this is equal to 0. Now, to get this, we actually have to use the definition as well. Because if you look at this expression and do the partial derivative with respect to y, the result is going to be the same as f sub yx. It's just that they are different at the origin. So for this right here, f sub x of y, when we use the definition, we are going to look at this part right here as our function, which is this, and then y is the variable. So when we use the definition, as h approaching 0, we will have to add h to the y. So here we have f sub x, and then 0, 0, but we add the h in the y, and then minus f sub x, 0, 0, and this is where we need that, and over h. Now for this right here, we look at this expression, plugging 0 into all the x's. This time though, that 0, we have something on the top. What is it? We put h into here, so we get negative h to the 5th power. And then on the bottom, put 0 into here, and then put h into here, so that is h squared, and then squared. And then minus that is 0 over another h. And remember to do this inside out. This right here is the limit as h approaching 0. The top is negative h to the 5th. The bottom here is h to the 4th, but we have another one, so that is h to the 5th. Well, we can cancel out the h to the 5th. So we just get negative 1 as h approaches negative as h approaches 0. The result is just negative 1. So this right here is negative 1. Now we'll do the same thing, but for this now. So here we go. We will get f sub y first. So look at this and take the partial derivative with respect to y. Use the quotient rule. So the bottom function right here, multiply by the derivative of the top with respect to y. So that's 1, and we have x cubed minus 3y squared times x. And then minus the top function times the derivative of the bottom with respect to y, and then all over the denominator squared. And then just distribute combined terms. So here we get x to the 5th, and then minus 3x cubed y squared plus y squared x cubed, so x cubed y squared, and then minus 3x y to the 4th, negative 2y times that, negative 2x cubed y squared, negative negative plus, and then 2x y to the 4th power over that. Whew, a lot of algebra, right? Okay. So on the top here we have x to the 5th, and then I believe this, okay, and that, and this, they all have x cubed y squared, so negative 3 plus 1, negative 2 minus 2, so it's negative 4x cubed y squared, and then lastly this and that, so that's negative 2, no, just negative x y to the 4th power over the denominator. Okay. Then, just like what we did earlier, we need f sub y at 0, 0, and use the definition, the limit as h approaching 0, and then f of 0, 0 plus h, and then minus f of 0, 0, and over h. So put 0 into all the x's, and then over that, so that will just be 0. And then, yeah, over h squared, something like that. Doesn't really matter, that's 0. And then this right here is 0. And then h over h. So that is 0. So the whole thing is equal to 0. Okay. Now, for this right here, f sub y of x, we look at this as our function. And then remember x is the variable, so we do the limit as h approaching 0, and we will have f sub y at 0 plus h, comma 0, and then minus f sub y of 0, 0 over h. So limit as h approach 0. Okay, this is plugging h into all the x's. So here we have the h to the 5th power, and the rest is 0, and then also do that right here. So it's h squared and then squared. I think you guys see it right now, right? And then this right here is just minus that 0 here, and then all divided by h. And remember, work this inside out. This is the limit as h approaches 0 of h to the 5th over h to the 4th and then another h. So for this right here, they cancel to be 1, and we just get 1. Alright, so this is different than what we got earlier, right? And now let me just summarize everything for you guys. So from the result that we have earlier, we saw that f sub xy at the origin is equal to -1, but f sub yx at the origin is equal to +1. That's why they are not equal. Why is that though? Well, here are some facts that I would like to write it down for you guys. Fact number 1. Well, in fact, if you look at f sub xy, so just look at the f sub x expression that we had earlier and take the partial derivative with respect to y, that will actually be equal to f sub yx. The expressions will be exactly the same. But this is only the same if xy not equal to 0, 0, because we have it right here. If it's at the origin, they are not equal. And now you might be wondering, why is that though? Because doesn't the Clairaut theorem says mixed partial derivatives are always equal? No, it's not always equal. It depends on the condition. And the condition is that, in this case here, f sub xy and f sub yx, in fact, they have the same expression. But anyway, so I'll just say this right here. This and that are not continuous at the origin. So when you don't have continuous mixed partial derivatives, well, you might run into that situation. So this right here is it. In my opinion, very cool example. That's it.